Hello everyone. So this is the very first lecture officially in the course on microprocessor systems design and interfacing. And as discussed in the previous session, we will be starting off with an interesting project. So this project is actually to build an 8-bit microcomputer using the logic gates or using your knowledge of digital circuitry which you are carrying from the previous semester. So the advantage of doing so, which is actually, as I said, it's slightly different from a typical microprocessor course, is like you will understand what is happening inside a microprocessor chip. Okay, so we call it as a microcomputer here, 8-bit microcomputer rather than an 8-bit microprocessor. The difference obviously you should be knowing by now, because here we are not looking at a single chip solution, right? Rather, it's more like a functionality test. So you will use discrete logic gates, logic ICs, integrated circuits, and then come up with an 8-bit microcomputer. So that's the idea. Obviously, you won't be implementing them or basically fabricating them, but we will be trying to simulate them using the LogiSim software, okay, as practice. So let's quickly dig into this without any further delay. Okay, so this is the idea. As I said, it's an 8-bit microcomputer from logic gates, and rather it's very specific or very correct to say it's a programmable calculator. Okay, because we are not going to implement a lot of functionalities like in a modern day computer system, but rather it just gives you a feel of it. So for that we will implement addition and subtraction operation only, and that's why it's okay to call it as a programmable calculator rather. And programmable is an important aspect, okay, because the name, as the name suggests, because we know that the significance of a microprocessor or a microcomputer is that it runs based on some instructions, some programs, right? So that's the important aspect. And we also briefly discussed about the block diagram perspective, and we know that the most important aspect or component of a microprocessor system, or even in this case an 8-bit microcomputer system, is the memory. Okay, and when we call memory, you should also understand that it is typically when we talk about memory, the thing that comes to our mind is the data, right? But in the case of a microprocessor or a microcomputer system, it's not just about data, it's also the program, the instructions also occupy the memory space. So pictorially you can think of something like this. So you have a big chunk of memory which may be physically located at different places. Okay, we have a separate session on the memory architecture and all at a later point of time, but assume that the memory locations are physically separated, but I can point them in a continuous addressing space, and then that memory gets divided into 2 or 3 parts. In this case, let's assume it to be 2. So this part will occupy the program, and then this part will occupy the data. So these are the data upon which these instructions or programs will act upon. So that's the understanding here. And of course so this will be again divided into so many locations as shown here, the data also. Okay, and each location will have an address, and then inside it will have a content, and some people actually call it as data itself. So this is a typical architecture, and in fact when we have a deeper understanding of this as we go forward. So just on a high level, it's a memory, and that memory can store data and can store program, and these are the programs which make decisions or make the computer to do certain things, right? So that's the idea here. And then of course you need a circuitry, right? I mean, to make things happen you need a digital circuitry, right? Otherwise you need somebody to execute, right? You have something stored in memory, you have some instructions in the memory, that instructions has to make things happen. So who will make that happen? That's a digital circuitry, right? And you can even think of that as something like control and execute. Okay, you have a control circuitry and you have an execution circuitry which does the job for you. So it is nothing but made up using the digital circuits, that whatever you learn, the combinational and the sequential circuits that you learn in the digital systems course, you will be utilizing that. And then of course we need a communication link between them, and that is something which is known in microprocessor or microcomputer world as bus. Okay, so bus is nothing but a set of wires. Okay, you can just imagine a set of wires connecting the memory to the digital circuitry is what we call typically as the bus. So basic important thing about the bus is like this is something sometimes the bottleneck of the speed of a computer system. Okay, so I'll tell an example. So in the case of a modern day system, the bus will be something like 32-bit or 64-bit. Okay, you might be using a 32-bit microprocessor or a 64-bit microprocessor in the modern day world. Here we are talking about an 8-bit, for example. So the bus size depends on that particularly. So if it's an 8-bit microcomputer, it typically has an 8-bit bus. Okay, so that's the thing. And then the rate at which the data transfers from the memory to the circuitry is also important, right? So that is limited by the bus speed. So most of the time the processor may be something like 2.6 gigahertz. That means giga operations per second it may be able to operate, but the bus may not be able to support that much. Bus even now are still operating in the range of mega samples per second or megabits per second. So it's actually pretty much reduced in that sense. Okay, so we will discuss about these aspects at a later point of time in a greater detail, but at this point you just need to understand that this is the very high level architectural overview of a microprocessor or a microcomputer system, where you have a memory, you have a digital circuitry, and then interconnected between them using buses. Okay, and now this is on the hardware side of it. Now think about something which is actually on the software side of it, because I said instructions, right? But then there are certain rules and regulations that we should follow, so that the third person using the thing should understand that this is what it means, right? So we need to have some programs, some software associated with it. So this software for the hardware, right? Whatever hardware that we are building. Okay, so this also has a certain hierarchy. So the way we write the software, we can do it very closer to the digital circuitry or very far away or a very high level stage compared to the hardware language. So that's why we call it as a hierarchy of software or hierarchy for software. And the very lowest level in that sense is something known as machine language. And when we say machine language, it is a language of zeros and ones. Okay, so that for a human to understand that, it's almost impossible. Okay, machines understands that only. It doesn't understand the way we write programs, for example in MATLAB, Python, Java, C++. It's something which we understand, but machine doesn't understand that. So that language, whatever we write, gets converted to machine language using compilers, assemblers, and linkers. So they will convert that English sort of language to language of zeros and ones, which we call as machine language. So if somebody can write a code in zeros and ones, the machine language, that will be the most optimized code that you can think of. Okay, so that's something which is interesting. And then the next level of slightly more comfortable to a human is what we can call as assembly language. So assembly language is again probably using the English sort of language that we are comfortable with. But having said that, it's not as user friendly as C or C++ or even higher level like Java, Python, or MATLAB. It is very specific to a microprocessor or a microcontroller system that you're going to use, but much comfortable, much easier for us than to code in using zeros and ones. So you will understand what is an assembly language, because you will be in fact coding in assembly language at the start, and you will write very optimized codes, and then you will understand that it's not easy to just use assembly language all the time, because it takes a lot of time. It's not that user friendly, and that's where you move to slightly higher level. And the next high level that is much more comfortable for a human to write a program is the high level language, which example is actually C or C++, for example. They are still not as very comfortable with a lot of APIs and all. It is still restricted, but it's much better than you write a program in assembly language. So there is something which is very important to notice here. The high level language is actually microprocessor agnostic. So that means you can write generic language and it gets converted to a particular microprocessor using the assemblers and the compilers that we employ there. Okay, so that takes care of that conversion. On the other hand, assembly language is very specific to the microprocessor architecture that you choose. So for example, in this course you are going to use a ARM Cortex M0 Plus microprocessor. So there is certain set of language that you can use to deploy programs in this particular microprocessor. So not let's say you choose another microprocessor, it will be another set of language that you need to use. So assembly language is very specific, or it is dependent on the microprocessor architecture that you choose or microprocessor that you choose. But high level language on the other hand is agnostic to that. It means you can write generic, and the assemblers and the linkers will take care of that conversion from the high level language to the assembly language. And then of course we'll revisit all these again later at some point when we discuss about the software architecture in detail, but this is a more like a high level overview. And then the next high level is something which all of us are very comfortable in working, and all of that makes us so lazy to work with, is the application level language. The example is Python and MATLAB that you use. Okay, so this is the most popular among all of us, right? So but imagine that for a machine to understand, it needs to go along this hierarchy. So we write a program in Python or MATLAB which gets converted to its C or C++ backend, and that probably is getting converted to assembly, sometimes directly to machine language. So the machines, when it comes to that level, it understands only that zeros and ones. Now I just want to reiterate again here, because all of us are digital circuitry and knowledgeable people. So whenever we say zero, it is literally meaning the ground or the zero voltage representation, right? And whenever you say one, for a software it is one, but for a hardware it looks like a 5 volt or a 3.3 volt, for example. Okay, so it's a high voltage, and zero means a low voltage. So that's the physical interpretation of it. So imagine the beauty here. So you're talking about something in the English language which is getting converted to zeros and ones, which means something to the hardware which is lying here, right? So here again, to reiterate, don't get lost, because we will revisit it again and again, so we will become very thorough about it. But the essential point that I want to convey here is there is a hardware architecture, and typically when we say hardware architecture, it consists of a memory, digital circuitry controlled by bus. Okay, so this is a layout that it has, and this hardware uses a software architecture, and this can be anywhere in this chain, but the unavoidable thing is basically the machine language. It has to be there because that's the only thing which can communicate with the hardware. So you can think of that hierarchy. Actually, you start with the high level, then it gets to the low level, then the machine language that communicates with the digital circuitry. Okay, so this machine language will sits in this program memory. So remember that. Okay, so we'll discuss about that. Okay, so don't worry. Okay, so let's move forward, and now I'll slowly introduce you to the very first project that I was talking about. So we will build our own 8-bit microcomputer from scratch, and we will be following the book Malvino. So you can download the PDF version if you want, and we are following the chapter on simple as possible computer 1. So if you see the Malvino and browse through the chapters, you have to spend time on this particular chapter, which is SAP 1, simple as possible computer 1. So this is what we're going to just replicate, and of course diversions are possible, but for the sake of understanding and for the sake of easy following, I'm just strictly following whatever is there in the textbook. You can actually vary a lot of things which your seniors have done that, and see the changes for yourself. Okay, now let's spend some time understanding this block diagram. This is our aim in the next 2 weeks at least, and you will be implementing this in Logisim. So that's the beauty, right? It's not just the theoretical side of it. You will get a real hands-on of the circuit, what is inside of each of these in a very detailed way. So just to give a very high overview, as a engineer, the most important thing is, first step is to see what all components are here. Okay, so we know this is an 8-bit, so the bus here is 8-bit. So the number 8 here means it is a set of 8 wires which is going from up top to bottom physically. Okay, so just imagine that. Then we have on the left hand side, we have a program counter. You already studied about program counter in your digital circuits, and this number wherever you see, it's a bit size. Okay, so this program counter is a 4-bit program counter. So basically it sort of counts from 0 0 0 0, so 0 0 0 0 all the way up to 1 1 1 1 is the expected values which will be coming here, and again it goes back to 0 0 0 and 1 1 1 1, right? So that is the basic functionality here in this particular case. Okay, So this program counter is connected to the 8-bit bus through 4 lines. Okay, then the question comes is, this is 8 lines and here only 4 lines are connected. What about the other lines which is expected to, maybe the most significant 4 lines which is there in the 8-bit bus? Where is it going? So that can be connected like don't care, right? It doesn't matter to this. The least significant 4 bits gets connected to the least significant 4 bit of the bus. That's the idea. And then there are certain signals that you're seeing over here like CP for example, EP for example. So those are control signals, and you can actually see these guys are coming from right here. So the EP here and the CP. So this is issued by a digital circuitry. So there is a digital circuitry we call as the control unit or the controller or the sequencer, which will be controlling the operation of this digital circuitry. They will release these signals and they are connected to these digital circuitry like point program counter in this case. And then you can see here, so this is LA bar, this is EA. So those are the control signals for this particular component known as accumulator. Okay, so all these signals are coming from, so when you wire the circuitry, you need to physically connect these 12 bits to their individual locations. So CP line should be connected, CP bit line should be connected to the CP in the program counter here. So as again, I'll just want to reiterate here, this is a counter, a simple up counter for example, which has 4 bits as the output. And then we have the lifeline. This is a synchronous circuit. So microprocessor is a synchronous circuit. It operates with respect to the clock, which is a lifeline of the system. So whenever the clock ticks, that means whenever the clock changes the value, either edge or the post high value to low value, some change is going to happen in this microprocessor system or microcomputer system. That's what precisely the workflow of the system, right, which we will explain at a later point of time. But you can see that most of these components here are connected with the clock. If there is no clock connected, that means it is an asynchronous circuitry. That's all. For example, the RAM, the memory, random access memory, is an asynchronous circuitry. Okay, so it doesn't need a clock to output something, because that's the important aspect. And then clear is just to reset. So all those things you already know. And then of course you should be aware of what this bar on top of the signals signifies. So that means it's an active low scenario. So for example, LM bar. Okay, so that means actually it is an active low signal. That means if it is 0 only, the input to this is 0 only, this particular guy will be activated. Okay, and then all these control signals are either to connect the component to the bus or the reverse direction. So you can see the direction of flow is from here to here in this case, but here to here in this case. So whenever we are getting the data from the bus to the particular component, we typically use this suffix L. I will again reiterate it later when we explain the circuitry, but I thought I'll explain the reasoning of these naming. So on the other hand, whenever we are putting the data from this guy to this, it will be either C. Okay, sorry, not that, E actually, this guy. Okay, so E. Similarly here EA, that means the component of accumulator is going to here, and L for example is for the data going from the bus back to the component. So L and E enable and load respectively. So enable means you are enabling the data transfer from the component to the bus. Load means you are loading the data from the bus to the component. So even if you forget now, you will anyway follow it when you make the circuitry. So that time it will become very clear to you. Okay, I'm not going to confuse you. Let's move on faster. So you have a program counter. Then you have a set of registers. So this is memory address register. So input and memory address register. So this is a register. This is another register. This is accumulator. This is again a register. There is a reason why it is known as an accumulator, which we will discuss at a later point of time. This is another register. This is also a register. So you have 1, 2, 3, 4, 5. So let me list down the components here. So you have one counter, right? And then 3 plus 2, 5 registers. You have one memory. In this case, it is RAM. So if you want to write it as memory, you can write that way, right? And then you have a control unit, so that inside of that there can be multiple circuitries. So I'm not going to discuss that now. We'll take it at a later point of time. And then we have one adder subtractor. So in generic terms it is arithmetic and logic unit, even though here in this our very simple programmable calculator sort of computer we are only doing addition and subtraction. We don't have the logical operation, so we can ignore that. But one ALU you can think of. And then of course there's a display unit to display the results of the operation. So essentially these are the important components that we can see over here. Okay, and just to give a brief explanation of what these things do so that it's pretty clear to you going forward. And one habit that I'm trying to follow throughout these lectures is I keep repeating things. That's just basically to make, because many of you may not be following it first time, but if I keep repeating it, you will be following it at a later point definitely, right? So that's the thing. So program counter, there's no confusion there, and there is some connection from program counter to this guy that is controlled by this EP. Okay, and CP is basically the you will understand later that it is just to make the program counter count up. Okay, something like that, and then clock clear, everything is clear to you. There is another one which will, there's a register, again this is a 4-bit register that will store the input data as well as the memory address. That's why the name it is, and the physical meaning of it we will discuss later. And then very important component, which is the memory. As we know, this is an important component of a microprocessor or a microcomputer system, and in this case it is a 16 cross 8 RAM. So what does that mean? It's important to understand that. So 16 cross 8 means 16 locations, 16 memory locations, and you have each location having 8-bit long data. Okay, so basically if I see memory as a continuous set of locations, so you'll have 16 of them. Okay, so this is 1, this is 2, this is 3, and up to that you'll have 16th one. And then the size of the data that you call is 8-bit. That is why it is 16 cross 8. Very important to understand. Okay, 16 memory locations, each location will store 8 bits of data. Okay. I hope it's clear. And then interesting aspect is like in a digital system we always start from 1 instead of 0 instead of 1. So this can be, we can call it a 0, this is 1, this is 2, and then of course this will become 15, and you represent that in digital it will be 0 0 0 0 0 0 0 1 0 0 1 0 all the way up to 1 1 1 1, right? So in that scenario you just imagine the address, how many bits are required to store the address? Only 4 bits, right? So 0 0 0 0 to 1 1 1 1, and that is why we have this memory address register. This stores these address locations, and that's why it has a 4-bit memory. And you see, it looks like 2 separate 4 lines are going here, but that's not the case. It's just to show that the data coming from program counter also is reaching here, as well as something else is reaching here. So that's the only meaning of it, which we will discuss later. I don't want to confuse, but the meaning of 16 cross 8, I hope it is very thorough in your mind now. 16 locations, and each location will have 8 bits of data. So that's the meaning of it. So let me erase again. And then some instruction register. You see here this input is 8, so that means this guy is 8-bit, and out of that 4 is going back to the bus and 4 is going to the control unit. So that's the beauty. So 4 set of wires are going here, 4 set of wires are going back to the bus. Okay, and then on the right hand side we have an accumulator, and it is a register again, as I said, and there's a reason why it is accumulated, because maybe I'll tell that reason here, and maybe I'll repeat it again. So why it is called as accumulator? Because it stores the data, original data, as well as the result from this guy. So the result from this guy, adder for example, it goes back to the bus and comes back to the register A. Some people call it as register A. Okay, and that is also known as accumulator because it stores the input to the adder as well as the output from the adder. That's why it keeps on accumulating the data. So that sort of meaning gives its name accumulator. Okay, I hope it's clear. So this is basically first input, this is another input. So register A and register B, those are the inputs to the adder or subtractor unit, and the result also will get stored in register A, and hence register A has a special name, accumulator. And also keep a look at the control units, which is also we will discuss as we discuss the working of this particular circuitry. But in this lecture my aim is just to introduce you to the building blocks of this circuitry. Okay, and then output value will be stored in this guy, and that will be displayed at the output. So this is the holistic picture. So it's very simple, even though at the start when I showed this circuitry it was a little vague to you. I hope it is pretty clear about what is the components that builds this circuit. So it is just counters, registers, memory, and ALU, and then together with some digital circuitries. That's what you have here. So I will end this lecture very soon, but before I end and go to the next lecture in the next video, or next session in the next video, I just wanted to introduce you to the software architecture also. So I told that this particular guy can store 8 bits, right? And then we know that only 4 bits are required for the address. There is remaining 4 bits, it needs to do something. So that leads to what are those 4 bits individually all about, right? So that's where I need to introduce the software architecture. Just like the previous slide, we talked about the hardware part and then about the software part. Here is where I'm going to introduce you to the software architecture of a microprocessor or a microcomputer system with an example. And this is language that you see over here: LDA, add, sub, out, HLT, for example. They are known as the assembly language. Okay, so remember, machine language, the next level which is comfortable for human to start with is the assembly language, and this is what I mean. So this is looks like English, but at the same time it has some meaning to it. So LDA, so in our particular project that you're going to do as part of the first part of this course, you will be using these 1, 2, 3, 4, 5 instructions or commands that you can think of. Okay, so LDA means, the meaning of it is load RAM data into accumulator. Okay, LDA, load the data from RAM into the accumulator. So whatever is there in the RAM, some address location, that has to be stored into accumulator. So you can actually think of something like LDA, it will only take 4 bits, and then there are remaining 4 bits. So let me call it as XXXX. So this XX will be the location of the RAM, the address of the RAM. The inside, whatever is there in this particular address location, remember the way I showed you the address locations, right? 00002 to 1111 was the address location. So whatever content in this particular location will have to be loaded to accumulators. That's the meaning of this particular instruction. So if you, in the program, if you encounter this particular line LDA XXXX, the literal meaning of that is, once this is executed, whatever content is there in this particular address, that will be reaching in the accumulator. So that's the meaning of it. Similarly, ADD means add, and what does it actually full means? Add RAM data to the accumulator. So again, ADD will be followed by a 4-bit address. So that address will have a data. That data will be actually added with the data in accumulator. So that's the meaning of it. So you'll have a resultant signal coming here. So register A will be having some value. Okay, register B. So that B should actually have this particular data. The RAM data should come to register B so that it can get added with the content in accumulator. So that's the meaning of it. Sub is also same. Subtract the RAM data given by the address location from the accumulator content. So that's the meaning. Out means you output the accumulator data to the output register. So that's the meaning of it. Whatever is there in the output of the accumulator or the content of accumulator, you can put it to the output registers for display. So whatever is coming to output register immediately will get displayed. That's the meaning of it. HLT means stop processing. So when you encounter HLT, it's like a break, right? You stop there. Okay, so that's something like that. You just stop there so that the program won't execute further. Just put a halt to the execution of the program. So that's the HLT. Now this is assembly language, but computers doesn't understand this, right? It only understands zeros and one. And this table actually shows, this is again not hard and fast rule. This is just designed by us. The book of Malvino has just given us this mapping. You can change it and see if you want, but let's follow this completely. So whenever we write LDA, it is mapped to 0000. So literally LDA has no meaning in a computer system, right? So if you encounter NDA, it looks like 0000 in the computer system. So for example, in the memory location, if I want to store, I'm just taking a simple example, LDA 0010. So what does it mean? It means that the data content in the location 0010 in the RAM should be loaded to accumulator. But how to store this data, this particular instruction in the RAM? It's not possible, right? We can't put LDA and all. So how does we do it? Let's say I want to store in this location. So you go to LDA, it means 0000. So that means 0000, that corresponds to this guy, and then this guy is 0010. So whenever computer encounters this line, it means that 0000 means LDA. So that means it has to load the content at this particular location. So this location will come somewhere here. So let's say this is 0010. Okay, so this is a memory location. So whatever is content which is present here, this guy has to be loaded to accumulator. Okay, it has to be loaded here. That's what the meaning of it. Don't worry, again we are going to do hands-on, so you'll understand it very thoroughly. So again I will reiterate this and will stop this lecture. So there is a hardware architecture which we will build using digital circuitry. There is a software architecture which we will follow as it is. And similarly for the Cortex M0 Plus, there are certain mnemonics like this which is set off much more than this, because this is a very simple computer. The one we are going to use is like a 32-bit microprocessor which has a lot more options. So number of mnemonics will be much higher. But this set of mnemonics that you use, which has their own binary representation, which we call as opcodes. Okay, so this particular set of mnemonics is what we call as assembly language, and then the opcodes is what we call as machine language. So I hope it's pretty clear to you. So slightly higher level is C, which we will not talk till some point of time. So we will be living in this world of assembly language, mnemonics and opcodes for at least half of this course. Okay, so definitely. So you'll be understanding it thoroughly, I hope, and you'll be enjoying it, I hope. And we will start off with the hands-on most probably next week. Okay, so that's the thing. So I'll end this lecture. So the takeaway from this particular lecture is like there is a certain architecture, hardware architecture that we need to build upon, and there is a certain software architecture we need to follow, and combining them we have a programmable calculator ready. So hopefully that is exciting you. So until we see in the next video, bye from my side. Thank you.